Hello everyone, so this was the Core Pure 1 Further Maths A2 exam, which I think was set on like the 25th of May, is that right? Does that look right? It was around there, it was midweek last week. It's now the 30th of May, so yeah, I'm just going to go through the paper basically. Um, Obviously, don't if you've done this paper, don't beat yourself up if you haven't got every question right. I thought it was a reasonably friendly paper if you compare it to some of the ones which have been sat in the last couple of years. It was more like the ones they used to set, say from 2017, 2016, 2015, which means probably the boundaries might be a little bit higher, but who knows? Because we've had COVID recently, and so that's disrupted a lot of schooling. I really don't know. Anyway, let's just go through the answers. So we're given that 2 minus 3i is a root to this particular cubic, and they want us to write down another root. And obviously it's a root to f of z equals 0. Incidentally, I was asked the other day, like, what is a root? What really is a root? Now, I've always looked at root as solution, but it is important to note that root often is, if we just talk about the roots of that function there, we take it to be the zeros of the function. That's what the Americans call it anyway, the zeros of the function. In other words, where the function equals 0, what is the value of z? So you're solving to find where it hits the, if you like, the x-axis, or in this case, the z-axis, if you like. But we're basically finding the values which make the equation 0. Okay, so we know that 2 minus 3i is a root to that, and hence we can just immediately write down the other root because roots occur in conjugate pairs. And so we have 2 plus 3i. And this was a lovely question to start with, and I suspect that many of you will have got all of it right. Okay, we've now got to solve f of z equals 0 completely. Now, the way I approached this was I was like, okay, I can do this in a number of ways, actually. I could write down z minus, open bracket, 2 plus 3i, and multiply that by z minus, open bracket, 2 minus 3i. But I'm actually going to use the sum and product of the roots, actually, because for our quadratic factor, we know it's got roots 2 plus 3i and 2 minus 3i. Now, the sum of the roots is clearly here going to be 4, and that should equal minus b over a if we write our quadratic in the form az squared plus bz plus c. Yeah, our product of the roots is going to equal, well, if you multiply these two together, I suppose you could quickly do it on a calculator, but it really isn't that difficult to do in your head because you're multiplying something by its conjugate. So you just need to do that squared plus that squared, and that's going to come to 13, and that equals c over a. And now if we let a equal 1, we're going to have the quadratic z squared minus 4z plus 13. I've now got the quadratic. I thought that was the most sensible way of doing this. Now, in order to find the third root, because they did ask for the third root after this, and they also asked for the value of a, actually, to find the third root, I'm just going to go, okay, well, I've got z squared minus 4z plus 13, and I'm going to look at what I need to multiply that by in order to make z cubed plus az plus 52. There should be various kind of hints, and it's also going to tell me the value of a as an added bonus. So clearly I need to multiply it by a z to give me z cubed minus 4z squared plus 13z. Okay, that's kind of nice because we've got some things here. But have you noticed they've got no z squared here? So this must be a plus 4 in order to get rid of the minus 4z squared here. This is the way I do division. I'm not really much of a long division fan. I find it weird and confusing when all we're trying to do is say we need a linear factor to multiply that to give me that. So I'm just kind of using common sense, really. Okay, that's going to give me minus 16z plus 52. And so what have we got here? We can see that overall, we've got f of z equals z squared minus 4z plus 13 multiplied by z plus 4. And hence the roots, if I can just write them down here, are going to be 2 plus 3i, 2 minus 3i, and minus 4. And so I've solved it completely there. And the value of a, by inspection, we can see that a must be equal to minus 16z plus 13z, which is minus 3. And the very, very last bit of the question was, can you plot these roots on the Argand diagram? Well, yes, I can. It's going to be 2 plus 3i, that's roughly there. I always wonder whether to write 3 or 3i on this diagram. Like, you know, do they mind? I don't think they mind either way. This is like the imaginary axis. This is the real axis. And so often we draw these as arrows as well, because they're basically like vectors, really similar to vectors. And then we've got -4 back here. And there we go. We've plotted those roots. Sometimes people do them as little stars as well, actually. Might be nice to show them nice and clearly. Apologies for how bad my diagram is there. But that was question 1. So it was really quite a nice, gentle sort of settler. I thought it wasn't too bad anyway. Didn't have too many weird aspects to it. Okay, question 2. We had 64 cosh 4x minus 64 cosh squared x minus 9 equals 0. Now, when you look at something like this, and especially when you're asked to solve it, find the values of x for which that's the case, hopefully you're very used to seeing quadratics in disguise by now. This is a quadratic in disguise. If we let cosh squared x, and it's, you know, you don't have to do it like this, but I like to let cosh squared x equal u, because then it becomes really obvious that this is a quadratic in disguise, because we'll have 64u squared minus 64u minus 9 equals 0. I can then go about factorizing it. You probably cheat on your calculator if you've got, you know, if you're under pressure in the exam. I think I did actually factorize this properly when I did it. And you get 8u minus 9 and 8u plus 1. So we get u equals 9/8, or u equals -1/8. Now remember, this doesn't really make much sense, this one. This clearly is going to offer us no solutions, because cosh squared x is u. So how could cosh squared x be -1/8 unless cosh squared x was imaginary, well, complex in some way? And they're not looking for complex roots here. We're just looking for the real roots of this equation. So we're going to work with a u is 9/8, and we're going to say, okay, cosh squared x is 9/8. Be careful when you square root this, because obviously you're going to get cosh x equals positive 3 over 2 root 2. You're also going to get cosh x is -3 over 2 root 2. I like to write them both down. Now, actually, once again, this is going to give us no solutions, and that's because, think of the cosh x graph. It looks very similar to x squared plus 1. It really does. Now, can that ever be equal to a negative number? No, the y coordinate is actually always greater than or equal to 1. So if this was a number which was, you know, under 1, we'd be in trouble. So we're going to go to this one, and we can use the r-cosh formulae, which do appear in the formula books, and the r-cosh formula. Can I call it? I'd rather use a different letter in some way, but r-cosh of x is going to be ln of x plus root, and then I believe it's x squared plus 1. Or is it x squared minus 1? I think it's x squared minus 1 exactly. That is actually in the formula book, and you can look it up. So what we're going to get here when we do r-cosh is ln of 3 over 2 root 2 plus the square root of, square that, you're going to get 9/8 minus 1. So that's 1/8 in the square root. And if you square root 1/8, you get 1 over 2 root 2. So you get 3 over 2 root 2 plus 1 over 2 root 2. Oh, by the way, you do actually have a plus or minus here, but I've always preferred to put the plus or minus at the start of the r-cosh, just because it's essentially symmetrical down here, and you're going to get this answer, but you also want this answer as well. So yeah, I think it's easier to do it like that. This is a graph y equals cosh x as well, if you're wondering what I'm drawing here. So we're looking for the x coordinates there. So yeah, we get 3 over 2 root 2 plus 1 over 2 root 2, which is 4 over 2 root 2, but it is a plus or minus. And that gives us, once you've simplified that, that's 2 over root 2, which is just root 2. So a nice way of writing it is a half ln 2. Is that the format they wanted? Oh yeah, they wanted it in the form q ln 2 as well. Now remember, I like to point out, I should have pointed it out in the first question actually, a lot of this paper you could have checked as you went, yeah? So when you get your answers there, why don't you use your equation solver on your Casio Calc and actually check these roots? I did, and they turned out right if A is -3. So it looked like I'd done that whole question right. Similar thing here, you know, anything you solve in maths, you can check. So that's exactly what I'm going to do literally right now because I haven't checked this one yet. So I'm just going to type in 0.5 ln 2. Calculator's going to remember that answer now. And then I'm going to type in 64. Now, where is cosh? I've forgotten where cosh is on this. I think it's under option hyperbolic function. Yeah, 2 cosh. So I'm doing 64 cosh answer to the power of 4. It will take me a little while to type it in, but I hope you don't mind just to check if the positive one's right. I'll assume the negative one is as well because that's always the case because cosh is an even function. 64 cosh, option calc 1. So just give me a moment. Squared. I'll pop that in. There we go. Brilliant. -9. I'm just going to press enter and it does equal 0. Good. So I can give that a little tick. I'm always keen to point out to students because I don't know about you, but I rush things and I make careless mistakes. I really do all the time. So if you're that kind of person, you want to be able to check every single question in every way you can. And that's, you know, that's definitely what you should do. Now, next we had a nice little integrating factor question. I thought it was a fair one as well, you know, as in not really weird. I like the integrating factor questions though, anyway. I just think it's a really clever trick. Okay, so when you see something like this, you should be thinking integrating factor straight away. And remember, integrating factor is any equation of the form dy by dx plus py equals q, where p and q are functions of x. I think that's important. Well, in that case, multiply by the integrating factor, which is e to the integral of p. Yeah, that's the trick, written down in extreme shorthand, but that is the trick we're looking for. So I'm just going to write dy by dx plus y tan x first, and that's going to equal, remember to divide everything by cos x, e to the 2x cos x. And then I'm going to start doing my integrating factor, because I need to integrate e to the power of the integral of tan dx, and so that's e to the power of ln sec x, and you can look that one up in the formula book if you like. And so clearly it's telling me I need to multiply by sec x, or 1 over cos x. Now that's going to give me sec x dy by dx plus y sec x tan x. I like that. Actually, I'm going to write it in that order as well, because I always remember that sec x differentiates to sec x tan x in that order. It kind of rhymes in my head, but it's in the formula book once again, equals e to the 2x. And then you can kind of do the reverse product rule trick with dy by dx, because what I'd need is y sec x here. Now, always do a quick sanity check because it's easier to do product rule in the other direction. If you were differentiating this product, you differentiate that, you get dy by dx, times it by that undifferentiated, you get this, plus, then you differentiate the sec x, you get the sec x tan x, then you times it by this undifferentiated, you get y sec x tan x. It's looking good. And hence you've got y sec x equals e to the tan x, e to the 2x, e to the tan x, got tan on the brain, integrated with respect to x. Now that's an easy one to integrate as well. So I'm now going to write this as y over cos x, I think, equals e to the 2x over 2 plus c. And hence, and I think it did ask for it in the form y equals f of x, so I better do that. Y equals e to the 2x over 2 cos x plus c cos x, yeah? And now they tell us that y equals 3 when x equals 0. And so that obviously allows us to find the arbitrary constant. So I'm going to plug in 3 equals e to the 0, that's a half, but cos of 0 is 1. So that is actually going to be a half. Cos of 0 is 1. So we've got a half plus c. So c is clearly 5 over 2. And so now I can write down e to the 2x over 2 cos x plus 5 over 2 cos x and I've got my particular solution rather than the general solution. Now, what we can do with that is we can determine the smallest positive value of x for which y is 0. That was the next question. Find the smallest positive value of x for which y is 0. So, okay, well, let's plug in y is 0, I guess. We're going to get a half cos x, I'm just factorising it for obvious reasons, e to the 2x plus 5. Okay, and if that's 0, then either cos x is 0 or e to the 2x plus 5 is 0. Now, it shouldn't take you too long to realise this actually doesn't have any solutions. You could do it like this and then learn it, but you can't learn a negative number, so that's no solutions. Or you could just think about the graph of e to the 2x plus 5, which definitely doesn't hit the x-axis. In fact, it's asymptotic to the line y equals 5. So, yeah, it's definitely going to give you no solutions there. And that's why the answer is x is pi over 2, which almost seems a little bit too, I don't know. Maybe I've made a mistake in that one, but it looks right to me. It looks like a nice straightforward one. If there's a mistake, I can't see it. Okay, let's try the next one. This one. This one was definitely where it was getting a little bit more cerebral. You know, you have to think about these ones and be slightly careful of lots of things. It was a method of differences, but it wasn't a typical method of differences, was it? It was definitely not what I would consider a typical method of differences. But I don't think it's too bad, though. They wanted to prove, we're going to try and prove this result using the method of differences, though. And I really do wonder if I'm allowed to do it the way I wanted to do it, but didn't do it. I'm going to work with the left-hand side first. I'm going to talk about sort of like two different ways you could do this because, well, firstly, when you're confused on any sigma question, write out the first few terms. You know, try and get a handle on what kind of sequence we're dealing with here. We're clearly going to be doing ln 3 over 1 first. Now, don't cancel that down because it might not allow you to see some obvious patterns. Okay, the next one's going to be one more on the top, one more on the bottom. So that's going to be 4 over 2 plus ln 5 over 3 plus ln 6 over 4. And I think we can all see where that pattern's going all the way up to. Now think of your last term. Sometimes it's helpful actually to think of the last two terms, the second from last term and the last term. Now we're going up to n, so we're going to be going up to ln of m plus 1 over m minus 1. Now, you know, I really wanted to do it like this because of log laws, you could just times them all together, yeah? But I'm not sure I would describe this as a method of differences, but I'm pretty sure they would accept this way of doing it. I just wanted to show you the way I wanted to do it was not the way I did it, just because that instruction to use a method of differences was really ringing in my ears. But I tell you what, the last term is going to be m plus 1 over m minus 1. And the second from last term is going to be, well, it's going to be one less here and one less here, yeah? Now just look at this pattern here. That one's going to cancel with that one. That one's going to cancel with that one. That one's going to cancel with that one. That one's going to cancel with that one, so on and so forth. So we're going to leave the first two on the bottom and therefore the last two on the top, because you're going to have the one before it cancelling, well, the one before that cancelling with that one, and then the one before that cancelling with that one. And so it's going to leave you with ln of n times m plus 1 over 2. That's the way I wanted to do it, but that's not really the method of differences. Well, what was, you know, what occurred to me is I'm not using a difference there. A difference is a subtraction. And so whilst I wanted to do it like that, I'm guessing the question wasn't really letting me do it like that. And so, okay, we'll do it with a method of differences, which is really the same method. It really is. So, okay, let's do it the way they want us to do it. I guess we've got ln3, I often write it down like this, ln3 minus ln1 plus ln4 minus ln2, because you can write this as a ln4 minus ln2, can't you? You can write this as a ln3 minus ln1. So I'm guessing this is what they wanted us to do. They'll probably give you the marks either way. I don't know. I really need to start working for the exam board so that I can see what they're actually allowing. I think it changes from the year to the year though, like, you know, what they actually will allow and won't allow. Once again, put dot 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 in there, but then put like plus ln n minus ln n minus 2 over ln n plus 1 minus ln n plus ln n, sorry, n minus 1, sorry. Let's get it right. Put my brackets round. Apologies for the terrible handwriting. And then we're going to have the cancellation working exactly the same way, essentially. Lum3 minus lum3, lum4 minus lum4, lum5 minus lum5, lun6 minus lun6. And then we're going to have exactly the same thing, but that, like the second from last one is going to cancel with that one, and the next from last before that is going to cancel with that one. And so that equals, you know, minus, if you like, minus lun2, because lun1 is 0, plus ln n plus ln n plus 1, and that equals ln n plus 1 over 2. But yeah, I think that's not as clear as the way I did it initially. Will they allow either? I mean, looking at the question now, it says use the method of differences to prove that. I'm just thinking if they were being really, really strict, they could say that the first method wasn't a method of differences, although it is a very similar approach to a telescoping sum, isn't it? We're just doing it with a product rather than the subtraction. We're using the log law property. Okay, part B was a bit tougher. It said, okay, they want us to find the sum from 51 to 100 of ln of r plus 1, r minus 1 to the power of 35. I saw some people like wondering about whether that 35 was to the power of the whole thing or just the thing after the ln. Personally, if I see that, I would always treat that as ln of x squared like that. And I don't think this situation is any different because we've just got ln of something to the power of something here. I think you should always make it really obvious if you're not having that squared, you're squaring everything. They would always use brackets in that case. So I'm not sure it was something you should have been worried about. There were some people who thought there was an ambiguity there. I'm not so sure. But I know what it's like if you're in the heat of the exam. I've got maximum sympathy. I really have for everyone who's worked through this paper. This is hard mathematics. It really is. First thing I did, I guess, was I wrote it like, you know, bringing the power down. But as you bring that power down, it's a constant. So you can take it outside the sigma, just like you can do with any integrals, because summations and integrals are very, very related. Okay, so we've got 35 sum ln r plus 1 I minus 1, but we're not starting at 2, and we need to start at 2 if we're to use the formula which we just worked out. And that's the thing which should tell you that it was definitely a 35 which you could bring down here, because then you can use part A's result. So always think, does it make sense? Can I use a result from before? So now this is the same as 35, and we'll go from 2 up to 100 so that we can use our formula. Ln of r plus 1 over r minus 1. But then we'll subtract the first 50 terms from 2 to 50 of ln r plus 1, r minus 1. And now I can use the prior result. And using that prior result, I'm going to get 35 ln of 100 times 101 over 2. That's because n here is 100, and we're doing n times n plus 1 over 2, minus ln of 50 times 51 over 2. And that gives me, now I actually got this wrong the first time I wrote it down because I wasn't using a calculator or anything, and I don't know what I did. I did something wrong. But it is actually 202 over 51, I believe. Yeah, and that's written in the format that they want. This is an interesting one because you might think, oh, I'll try and check this, but somebody mentioned on some of the things I was reading that I don't think the calculator works. So let's see, just because the numbers are too big, and maybe they've done that on purpose so you can't check, because it is the kind of like question where maybe they want you to, you know, just not know. I'm going to type it into my calculator right now and just see if it comes up with the answer, or, you know, if I have to wait almost forever and a day and then it eventually says no, maths error or whatever it's saying. I can't actually get it in the Sigma at the moment, so I can't type the function in. Oh, come on. Give me a moment. I'm just trying to. Okay, I'm going to try that afterwards, but I believe that you can't actually work this out using a calculator, which is interesting. So they obviously wanted you to do it properly. Note that even if you've got part A, not managed to get part A right, you can do part B still here, because part A was a show that question. Okay, let's just do one more question before the end of part one. It was a matrices question, and it was one where I think we had to find an inverse of a matrix, but because there's A's involved, we cannot use our nifty calculators, which is fair enough, really, because they want you to know the technique for finding a 3 by 3 inverse. And it is a long old process, isn't it? And it's hard not to do it without making a mistake. Now, all we had to do in part A actually was show that it was non-singular. Prove it's non-singular. Well, if it's non-singular, then it means the determinant can never equal 0. So let's find a determinant. Now, the determinant is also the first line of working you would do for finding the inverse as well. But let's just write it down. 2, 3, 0, 4A2. Okay, if I'm finding the determinant of that matrix, then what I'm going to do is essentially the very first line of working for finding the inverse. So you sort of like imagine doing 3 times 2 minus 0 times a, but you also times by this one. So we're going to do a times by 6. Then we're going to do, I always write down minus next because it's always a minus, and I forget that it's always a minus. Can I just take off that line I've drawn a matrix because it's going to put me off? Ooh. Okay, so we've got firstly a times 6, and then we're going to have minus 2 times, and we need to do 2 times 2 minus 0 times 4, and so that's minus 2 times 4. And then we need to do plus, but then it's going to be minus 3 times 2 times a minus 3 times 4, which is minus 12. And this is going to give us 6a minus 6a, but then we've got minus 8 plus 36, and so we end up with 28. And that's our determinant, and it is clearly independent of the value of a, which is nice. And it proves it's non-singular. It doesn't equal 0, so it's non-singular for all values of a, because it's independent of a. So it's non-singular for all a, which are members of the reals. There we go. Okay, right, part B, and this was all it was, and also this is another one you could sort of like do a quick little check. Sorry, there's a spider on my monitor. Let me just flick it off. Sorry, Mr. Spider. There we go, he's gone. Okay, right, right, what do you need for the inverse? You need the minus first, the matrix of minus. Okay, make this matrix nice and big because some of these are going to be in terms of A. Now, your first values will be exactly what I've got in the brackets here. 6, 4, and 2a minus 12, which makes things a bit quicker. Then we're going to have to ignore these lines, and I'm going to do 4 minus minus 3a, which is going to be 4 plus 3a. Then I'm going to sort of imagine a cross here and here. I'm going to do 2a minus minus 12, which is 2a plus 12. And then I'm going to ignore this line here and here, and I'm going to do a squared minus 8. Let me just check I've got that. A squared minus 8. Yeah, that looks good. That spider's still there. I'm going to leave him be. Now I'm going to do the bottom row. So I'm going to get 0 minus minus 9, which is 9. And then I'm going to do 0 minus minus 6, which is 6. And then lastly here, I'm going to do 3a minus 4. Okay, that's the minus. And in many ways, that's the bit where mistakes normally creep in for obvious reasons. Okay, now we've got the cofactors. That's just where you do the diamond shape. So let's do the cofactors. Still well worth doing, even though the temptation is to do two things in one go with the cofactors of C transpose. But honestly, after many times getting it wrong doing it like that, I don't do it like that anymore. Don't rush things. 2a plus 12, a minus 8 minus a squared, and then 9 minus 6, 3a minus 4. So we've got a little diamond change of sign there going on. Okay, finally we can do C transpose and then multiply it by 1 over the determinant at the end. C transpose, this is like cofactors transpose. Okay, well, all I've got to do is write all rows as columns and columns as rows. I'm going to get 6 minus 4, 2a minus 12. I swear I do this a different way of looking at it each time. And then minus 4 minus 3a, 2a plus 12, and 8 minus a squared. And then lastly 9 minus 6 and 3a minus 4. Cool. And then all you've got to do for the inverse of m is multiply it by 1 over the determinant, and the determinant was 28. So that's going to be 1 over 28, 6 minus 4 minus 3a, and then that's 9, and minus 4, 2a plus 12. You don't have to times the 1 over 28 in. They're perfectly happy for you to leave it out. 2a minus 12, and 8 minus a squared, and 3a minus 4. Now I'm relatively confident with my answer here because I like to check things, yeah? And all I did was I went back to the question and I set a equal to 2 arbitrarily. And then I used my calculator function to find the inverse of the matrix when a is 2. And it came up with this answer with a equals 2 substituted in. So it's like a very, very kind of casual check for your answers. And as you can see there, I think 3 or 4 questions out of 5 so far, we've been able to check our answer relatively quickly in the exam. Okay, I hope this first part of the video was useful. I hope that I hope it's gone really well for you, that exam. And yeah, I'll be posting up part 2 soon. All the best. Bye bye.